Exponential functions. So looking at an exponential function, we need to remember the following properties. If I've got the same base raised to two different exponents, they'll only be equal if the exponents are equal. Because a number raised to a power is a unique real number for each x that I plug into that expression. If this exponent is less than that exponent, then this inequality will be true when a is bigger than 1, when the base is bigger than 1. And if this exponent is less than this exponent, this inequality will be true when we're dealing with a fractional value of a, number between 0 and 1. Then our exponential function has base a, where a is some real number, and a variable exponent. The a has to be positive and not equal to 1. So I want to determine the domain and range and graph 2 to the x. So we'll make a table of values. So if I look at 2 to the negative 2 power, we're plotting in values of x. So 2 to the negative 2 power. You remember a negative exponent means 1 over 2 squared. So that would be 1 over 2 squared is 4. So 1/4. 1/4 as a decimal would be 0.25. So that's this value here. 2 to the negative 1 would be 1/2. 2 to the 0 would be 1. 2 to the first is 2. 2 squared is 4. 2 cubed is 8. Plot those points and we end up with a curve that looks like this. Notice this is true for any value of x. I can plug in and I'll get a real value. So any negative number, 0, positive number, my domain is all real numbers. But the range, I'm only ever going to get back positive numbers because look what happened when I plugged in these negative numbers. It made a fraction, but it's still positive. So my range is 0 to infinity. As x gets large, we're going out this way on the axis. Look at what's going on with the y. The y is getting bigger. And we can see that here by plotting some values in our calculator. If I plug in bigger and bigger values of x, I see I get larger and larger values of y back. As x approaches negative infinity, I'm going this way along the graph. We're getting closer and closer to the line y equals 0. The y approaches 0. And I can see that when I plug in small values, I'm getting back decimals closer and closer to 0. Let's do the same thing with 1/2 to the x. So again, we're going to plot a table of values. So if I do 1/2 to the negative 3, 1/2 to the negative 3 would be 1 over 1/2 cubed, or 1 over 1 cubed is 1, 2 cubed is 8. And then, of course, when we divide by a fraction, we invert and multiply, so it becomes an 8. 1/2 to the negative 2 is 4. 1/2 to the negative 1 is 2. 1/2 to the 0 is 1. 1/2 to the first is 1/2. 1/2 squared is 1/4, and so on. We have the same basic shape, but notice it's pointed in the other direction. So again, I'm looking at a domain of all real numbers. I can plug in any x value. My range is just the positives. But take a look at what's happening here. As the x gets large, as I'm going out this way on the graph, the y is going close to 0. As the x approaches negative infinity, I'm going this way on the graph, my y's are getting bigger, so the y approaches positive infinity. And we can see that with the table of values. For negative x plugged in, we're getting big. For positive x plugged in, we're getting really close to 0. All right, so when the base is bigger than 1, it's going to look like 2 to the x. It'll have this general shape to it. My domain will be all real numbers. The range is the positive. It'll always pass through that point 0, 1, unless I perform transformations on the graph. And I'm always increasing. When it's between 0 and 1 for the base, it's going to look like 1/2 to the x. Again, domain all real numbers, range 0 to infinity. I'll pass through that point 0, 1 unless I apply graph transformations to it. And it's always decreasing. Again, both have the horizontal asymptote at y equals 0, but this one is on the left side of the graph, whereas the previous one was on the left side of the graph. This one was on the right side of the graph. Let's graph negative 2 to the x. Well, I can do this with transformations. This is a negative in front of the function, so it flips it up over the x-axis. So my domain is still all real numbers, but my range is negative infinity to 0. Let's graph 2 to the x plus 3. This is another transformation on 2 to the x. I'm adding inside the function, so that's a shift to the left. So if I shift left 3, it looks like this. My domain stays the same and the range stays the same. 2 to the x plus 3, the plus 3 is on the outside of the function, so that's a vertical shift. I'm shifting up. Now, if I shift up, the domain stays the same, but the range shifts up. So the range is 3 to infinity. Notice that also shifts up that horizontal asymptote. So my new horizontal asymptote is the line y equals 3 right here on the graph, is where we're heading to as x approaches negative. Now, I can use the knowledge that we reviewed at the beginning to solve exponential properties. Remember, we said if I have a to the b equals a to the c, that's only true if the exponents are equal. So if I can write these as having the same base, I can equate their exponents. Well, 125 is 5 cubed, and 625 is 5 to the 4th. So I can write this as 5 to the 3x equals 5 to the 4. So the exponents must be the same. 3x must equal 4. So that means x must be 4/3. You can verify that on your calculator. Let's do the same thing here. So 27 can be rewritten as 3 cubed. And 81 would be 3 to the 4th. Now, this is the same thing as 1/3 to the 3x. I want the bases to be exactly the same, so I get rid of this fraction by making the exponent negative. So here we get negative 3x equals 4 when we equate the exponents. So x is a negative 4/3. Again, you can verify that on your calculator. All right, let's look at this. 1.5 is 3 halves to the x plus 3. 9/4 would be 3 halves squared. And then when I have a power to a power, I multiply those exponents. So I'd have 3 halves to the x plus 3 equals 3 halves to the 2x. Now set them equal to one another. X plus 3 equals 2x. Subtract x over, and we get x is 3. Now, compound interest involves an exponent. Remember that simple interest is just principal times rate times time. So if I do that for the first year, I would be adding that back to the principal. So I can factor out the principal, and I get principal times 1 plus r. But on the second year, we'd be adding again. And notice it becomes 1 plus r squared. And so on down to the nth year. So in general, our compound interest formula is principal times 1 plus the rate divided by the number of times we're compounding raised to the exponent, number of times we're compounding times the years that we have the investment. If $1,000, okay, that's the P, is invested in an annual 3.2%, so R, we would change that to a decimal, 0.032, compounded quarterly, so that N is 4. How much will be in the account? 8 years, so T is 8, no withdrawals are made. So our formula was A equals P times 1 plus R over N to the NT. So that's 1,000, 1 plus 0.032 over 4 to the 4 times 8. So to evaluate that, we're going to plug that directly into our calculator. So I'm going to go 1,000, 1 plus 0.032 divided by 4, close the parentheses, to the 8 times 4. And we get 1,290 and 44 cents. This is money, so we round to 2 decimals. Okay, so the principal was 1,000, so if I subtract 1,000, we'll answer the second question. Interest is $290.44. Now, E is an irrational number, just like pi is an irrational number, 3.14-ish. E is 2.71828, and so on. We use E in continuously compounded interest. It's principal times e to the rate times time. If $1,000 is deposited in an account paying 3.2% compounded continuously for 8 years, all right, so we're compounding continuously. The amount in the account will be the principal, 1,000, times e to the rate is 0.032 times 8 years. So again, I'm going to go to my calculator to figure that out. So we come over here and we go 1,000 E. So you have the E key right here. I'm going to hit second and the LN key, and then we're going to go 0.032 times 8. Notice that I get back slightly more money than I do compounding 4 times a year. Compounding continuously is compounding every instant of time, so it should be more money. So it's $1,291.75.